Okie doke. So, the most basic form of the DHSS model with no capital depreciation, cake, so no extraction costs, and no technological change. It really can't fit at all the data we see about non-renewable resources today and going back for the last couple of hundred years or more. We looked at data from 100 years, but but could it still tell us interesting things about the future? Okay, let's have a quick look at that question. I can give you a quick preview of the answer. No. Okay. So here's the model. I've got rid of the cake now and we've got oil, but it's still, the idea is there's no extraction costs. And I put some functional forms in. We've got labor supply, we've got production of this single good, which is illustrated by a hammer. Some of it goes to consumption, some of it goes to the capital stock, which is used for more production. We've got this flow of cake or oil. We've got a production function in here, which is Cobb-Douglas. We've got no technological change, and we've got this capital accumulation function. K dot is I, which is also y minus c, minus delta k. But we're going to set delta to 0. Okay, and then Solo was interested in the question, could we, in theory, maintain constant consumption in an economy like this? And the short answer is that we can, if beta is not too big. Basically, it turns out, and I'm not going to go through this, you can see it in the paper, Hoteling's equity paper, section 8. If beta is less than alpha, we can do it. Okay. Why does this make sense? Okay. So we've basically got two stocks of capital. We've got the non-renewable resource and we've got the human-made capital. And clearly the non-renewable resource, the stock of that, can only go down. And that means in the long run, the flow of that also has to go down, right? So if we're going to maintain constant consumption, clearly we're going to have to, in infinite time, right, we're going to have to boost the capital stock. So to compensate for the reduced flows of R, we're going to have to raise K, which means we're going to have to invest. But if beta, the bigger beta is relative to alpha, the trickier that is going to get, right? Because when beta is big, the resource is very important for production. When alpha is small, capital is less important. So clearly it makes it harder to compensate for falls in R by boosting K. Okay, and when we do the math, it turns out that as long as beta is larger than alpha, I can't remember if they can be equal. We're okay, we can do it. Okay. What are the policy conclusions from this? Well, if you believe this model is a good representation of the economy, then as Solo discusses, it's actually quite tricky, because it's like, how do you actually make sure that the right level of investment is performed? It's not totally straightforward, right? What about the role of delta? Let me just check what I've got on the slides here. I think we'll park delta, but I just mentioned for now that delta here is 0. Okay, we'll come back to it because this is a big problem. But before that, let's just say something briefly about Hartwig, because that is another very, very famous paper in this literature. Hartwig's idea was, if through investment in human-made capital we maintain constant overall capital stocks, then we sustain utility without technological progress. So basically, if this is a capital stock, this is a capital stock. If the total value of the capital stock stays the same, then we're fine. Okay. And then the idea is that maybe we can do that by investing the resource rents. So the resource rent is what we have to pay for the non-renewable resource, even though it costs nothing to extract it. So what these firms have to pay in a perfect market for the resource is its scarcity rent, or the resource rent. And that's what goes up at the rate rho, at the discount rate here. So the basic idea is, look, we're using up one stock of capital, and that's costing that resource rent. If we take that rent and invest it in the other stock of capital, then the total value of the capital stock will stay the same and we'll be fine. Okay, as long as that's true, we will be fine. But there are two huge caveats to this. Let me just check again the slides. Yeah, okay, I'm not sure this slide. Okay, there are two huge caveats to this. The first one is that this requires that there's no depreciation of the human-made capital stock. Okay, so the idea is the resource rents are compensating for the loss of this capital stock. We use those to build up this capital stock. It should be fine. But if in addition to this going down, this depreciates, they go rusty, fall apart, whatever, then we've got another source of loss of capital, right? So then the resource rents are not going to be enough. Okay, so if delta is greater than 0, it's not going to be enough. The other problem is that even if we can maintain capital for a while, we might not be able to do so indefinitely. We can easily come up with paths where we depreciate this, or we use up this, invest a lot in this, and maintain constant consumption for a while, and then we sort of fall off the cliff. Suddenly we can't do it, we can't manage any longer. The capital stock is very large, it takes a lot of effort to maintain it. This is almost empty, the reservoir here. We've managed to keep constant consumption for a long time, and then suddenly it's like we can't do this anymore, we fall off the cliff. Okay, let's see. So assume delta is greater than 0. Will resource rents be enough to ensure constant net capital? No. Assume we ensure for some period constant net capital. What happens in the long run? If delta is greater than 0, we're done for. We can never maintain constant consumption in the long run. So we're shifting capital from this stock, which doesn't depreciate, to this stock, which does. We've got nothing else to compensate, no technological change or anything else. Clearly, as this runs down and this depreciates, we're gonna end up with falling consumption, unsustainability. Okay, so if we assume delta is greater than 0, there's no chance whatsoever of sustainability in this setup. The inhabitants of the model economy are doomed. To resuscitate the model, we need to assume no depreciation. which of course makes no sense. If we build machines and things and use them to make stuff, we know that they will depreciate. But could we say, well, capital is some kind of proxy for knowledge actually, and knowledge doesn't depreciate? Well, there's a huge problem with that. Because if we're actually talking about knowledge, we should model research and knowledge accumulation, not capital accumulation, right? This is a model of capital accumulation. Knowledge accumulation is very different, needs a different model. Okay. Right. And I think we're winding up. Yeah. We're winding up this video very shortly. How am I doing for time? Not too bad. So yeah, I'm not a big fan of the DHSS model. I mean, of course, it's 50 years ago, it's fine. It's just a shame that it sort of dominated the literature for 40 of the last 50 years. The assumption of zero extraction cost isn't realistic, and that's what is fundamentally behind the resource price prediction that is contrary to the evidence. The assumption of no depreciation of human-made capital gives an excessive role to physical capital accumulation and distracts attention from the key role of knowledge accumulation. Okay. And that is the end of that, and then there'll be a short video on like why, if this approach has all these weaknesses, why was it ever used? Okay, that will be the last video on DHSS.